Um, so I'm going to show you some more spatial statistics on these ground motion residuals, but from kind of, the work was all done for slightly different purposes, so the approach is different, but I think the punchline is it's kind of consistent with everything that was shown this morning. So that the way we were looking at some of this data, so here's kind of the graphic illustration to think about what's going on. So we were taking kind of total within event residuals, so kind of observations minus predictions minus event terms, and that's kind of color-coded here, but and kind of normalized by the phi, so number of standard deviations away from the predictions. And so we were interested in the kind of the spatial clustering of kind of high residuals and low residuals. So the statistical way that we looked at it was to kind of take pairs of observations with a given separation distance and look at kind of empirical correlation. So this is a whole bunch of observations of residuals with a given separation distance within some tolerance. Look at the correlation. So kind of marginally, this epsilon 1, this is normalized, so it's a little inconsistent with that equation, has a standard deviation of 1. If you observed an epsilon at another station, you'd have kind of a reduced standard deviation there. So you do that for kind of separation distances that kind of vary larger and smaller, and look at how those correlations change with separation distance. So here are kind of 4 plots of different recent models, a couple of my students and some by Goda and Hong. So this is kind of those correlation coefficients with separation distance. Some things to observe, I guess, are that by 20 kilometers plus, you've got very little correlation remaining with this kind of approach. In less than 5 kilometers, they're not particularly well constrained. There's not tons of observations at those separation distances, so that's why the models kind of vary more widely there. None of these studies saw any dependence on kind of earthquake magnitude. There's no kind of closeness index azimuth type parameterization here. In the way this was approached, there was not kind of detectable differences there. I don't think that means that there are no trends. It just is not detectable with this kind of brute force approach at this data. In the 2009 paper with JRM, we did note some differences from event to event based on apparent kind of heterogeneity in site conditions, which got mentioned earlier this morning already. I'll show you that a little extra in just a second. So these correlations then kind of, again, imply kind of a conditional reduction in standard deviations if you have an observation nearby. So some quick calculations. So the idea would be, if you had, this is kind of in plan view, if you had a rupture and you had an observation, so you knew the residuals at that site, and you were interested in kind of a conditional standard deviation at some distance away, and it doesn't matter kind of which direction you are away because of the parameterization here. So obviously there's something lost in terms of kind of capturing a path effect out of this. Here is what the conditional standard deviations look like with those different models. And I think this JRM and Baker in red, I think it was kind of forced to a full correlation. I think it was just, it's a model feature rather than data-driven. The other cases you see are in it kind of, so this is kind of the total phi here, and then that's the Boren-Atkinson phi at 1 second just for a reference value. And you're down to about 2/3 at kind of 0 separation distance, or as you head towards 0. So I think there's kind of more reduction than that possible if you were to track azimuths and things more carefully as well. But that kind of 2/3, 50% reduction that was seen in some of these other studies is kind of consistent with this, I think. Then so another plot, if you had 2 stations, kind of on opposite sides, both with the same separation distance. So here I took off the alternate model, so the blue was the same blue line as the previous slide, and with 1 station at a given separation distance. And then a second station at the same separation distance, kind of on the opposite side, would give you some further reduction according to this model. And if one station is closer than the other, kind of the closer station tends to dominate, so the kind of equal distance case is the most interesting. And if those stations are kind of both on the same side of the location you're interested in, you won't get this much benefit as well. So that's kind of a maximum benefit you might get from 2 stations at a given separation distance. I came kind of with the assumption that those numbers, those kind of relative reductions here might be a useful ballpark.
So just to put this all in the framework, we've been talking about at a site with different sources and
right.
how the source moves.
Yep.
Now it's a source and you're moving the site.
Right.
So it's a trade-off between those, which
right.
is fine because you have a lot more data to work with too, right?
Right.
There's a whole lot of advantages. So we are essentially saying, if we want to try to deal with this, moving the site a few kilometers would have been the same as shoving the source a few kilometers at the same site. I mean, that's kind of what we have to try to assume to bring those two numbers together, right?
Yeah, so that's right. So we did it this way because the data is
Right.
easy to work with. I think because of the way this is set up, we're getting a mix of kind of a shared path, but also there's a bit of a shared site term
Right,
in here as well.
right.
And so there, I think moving the source, I'm not sure perfectly reconciles.
Well, let's say after we've already taken the site out.
Okay, yeah.
Because we're going from VSSs down to fee single paths.
Right.
And so that deviation, I mean, in some contexts, if you make that assumption, at least we
Yep.
could greatly expand our data set.
Right.
Which is what you're doing.
Right, right. Yeah, so some other assumptions have to be made to translate this.
Right.
To me, I think it's reassuring that it's kind of consistent with these kind of more direct studies. I don't see that there's a benefit to kind of moving this direction at the exclusion of these other approaches.
It would be complementary, right?
Yeah,
To pull them
yeah, I
both
think so.
together.
And as I was sitting here this morning, I think it would be interesting to do these same statistics on residuals that were corrected for a site term to see kind of if the kind of the spatial structure held up or if what happened. And here's the actual extra slides I just threw in this morning. So the idea, the thing I wanted to show you here is, so here's kind of this is 1 minus correlation coefficients with separation distance, and this is the PGA kind of total within event residuals from Chi-Chi. And so you go out to some distance, in this case about 50 kilometers, at which you've kind of lost all your correlation. So that range there is plotted over here versus the spectral period, and one line for each earthquake. And sorry, I just grabbed it quick, so I don't have a color version. But the one that was maybe that's worth highlighting is Chi-Chi, which is the line with no symbol on it. So it came in with, it's got kind of higher ranges at long periods, and also at short periods. Most of the other events are kind of down at 10 or 20 kilometers. You've lost all your correlation distance, or your correlation. I think this is ANZA was kind of not particularly well sampled, so that might just be some noise. But Chi-Chi seemed to have kind of more spatial coherence than the others. And to me, so we speculated that was potentially kind of heterogeneity or homogeneity in site conditions, so that as your site terms vary spatially, that appears as kind of more spatial correlation here than kind of a Southern California more varying site condition data set. So
But we could give you all of the site terms removed. I think that would be.
we could rerun this very
Yeah,
quickly.
rerun. Okay.
Yeah, we'd be happy to do that.
And also maybe do it for
You need
Japan.
a microphone. Use that.
Also maybe do it
Yeah.
for Japan.
So this was 2009. So this was primarily NGA1 data. For 2013, we redid it with NGA2 data. So these are the cases we had studied already. So we've got all the geometries and the residuals. But if we had site-corrected residuals, we'd just rerun the same code and get the same models back out.
So have you looked to see whether, especially at low frequency, if there's a systematic effect of the size of the earthquake itself on that?
We really thought that kind of the dimension of the rupture versus the dimension of these would have a strong impact, and we weren't able to detect it. I think
But if you go back to your table,
like
that figure,
right,
most of those aren't very big,
that's right,
except for Chi-Chi, which is much bigger than the rest of them,
that's right.
and
But-
it has the longest distance at low frequency.
Right, so there's one point up in the upper right corner. I think, I'm trying to remember which else. So Northridge, I think, had particularly low separation distances, which was kind of the intermediate magnitude here. I think that the geology is so different in those two cases that it was hard to extract site homogeneity from magnitude. Physically, it certainly must be there, but it didn't kind of jump out strongly in this statistics.
So from the CyberShake data, Manuel had checked the 6.5 versus the 8, so it's not 4s versus 8, but there is similar. So there was no scaling differences in the path effects if we use the closest point of the main of the large rupture to quantify as a path there.
We tried also with some simulations, I think from Rob Bear's Puente Hill simulations, to look at some distance dependence as well, binning kind of nearby sites versus more distant sites, and didn't pull out kind of strong effects that way either.
Okay, any other questions for Tom?
In Japan, I think it's Yokohama has an extremely dense citywide network. Have you considered using that data?
Both of these studies were directly off of the NGA data sets, so we didn't try to reprocess or reselect anything.
But
we didn't.
This Japanese data set is run by the city. It's kind of outside their normal set of networks, but hundreds of stations within the city region.
Yeah, clearly these models are not well constrained there. So
also, it's 100-meter spacing.
okay. Yeah, I mean that's where these are not well constrained. That wasn't really the problem we were trying to get at. This was, for other reasons, but that would be a nice refinement.
Brian, you had a question?
Yeah. So my question is, when we, in NGA West 2, when we calculate phi, we assume it's spatially uncorrelated. All the residual are spatially uncorrelated. Now you're showing that there is spatial correlation. So how that's going to impact our estimates on phi?
Right. Yeah, that's another topic.
Yeah, we want the fee at the top, but that's where,
Right.
if you took the average from all that data, because most of it is
Right.
at the longer end, I think it's
So-
not so bad, but you're right, they're correlated, so we have an underestimation due to
Right.
the correlation.
Right, yeah, so I mean, we've tried it, yeah, so that basically just changes your likelihood function when you're, instead of having this kind of block likelihood function. So we've tried rerunning that, and it only makes a difference when you've got an event that was recorded at relatively small spatial extent. Once you've got well-separated stations, it kind of goes away. But it did kind of push down the taus and push up the fees a little bit. That some of what looks like an event term could potentially be kind of spatially correlated single station terms. It wasn't a strong effect, but I think maybe more for kind of portfolio loss modeling.
Last question for Gabe, and then we're gonna have our break.
Jack, did you look for deviation from an isotropic correlation structure?
We did, so we tried to kind of go normal to the fault and parallel. We didn't detect anything strong. Again, it's just a very sparse data set to try to add these extra predictors in there. Because again, physically you'd anticipate something with regard to kind of shape paths. But it didn't pop out strongly out of any of this.
But from this, you could provide us the flat value, the sigma at large distances compared to the computed sigma as a correction factor, saying we are, let's say, 5% low on our standard deviation or something like that, right? Yeah. Even if you're running a likelihood model.
Oh, to refit the model.
Just
right.
spit out a fee and
That's right.
compare that to the crude one where they're just assumed to be independent and give the ratio, because
Yeah.
that can be a way to scale it up.
Yeah, we have that from 2000, from the NGA1 data set.
Yeah, but repeat it with this data set would be
Absolutely.
the great thing. Okay.
Sure.
All right, we're actually at our break time, so thank you, Jack.